Okay, in the last video we looked at different designations for fasteners. We looked at the lengths, the size of the bolts, the different types. We looked at set screws versus cap screws versus machine screws, how they're measured, and a bunch of information on that. This video we're going to look at screw thread terminology. So we're going to look at all the different kind of more technical terms and look at some of the different properties and screw thread theories that really truly understand how these things work, so that when you're maintaining a machine you can reference that knowledge and fix machines. So the first terminology that I want to review is internal and external threads. So this one here, this nut, is an internal thread, and this cap screw is an external thread. External threads are referenced as an A thread, and internal threads are referenced as a B thread. So you can think of it as A, B. So in the different classes of fits, this could be a 1A, it could be a 2A, it could be a 3A type fit, and for this nut we could also have a 1B, a 2B, and a 3B fit, going from loose to tight as far as interference or as far as the fit goes between those two fasteners. Same thing from here. We can go from loose to tight. Okay, so that's the first thing, external, internal threads. It's pretty straightforward. But let's look at some of the terms that describe screw threads, because if you're machining, referencing, talking about fixing them, it's really good, important stuff to know. All right, so let's look at some of these different terms and definitions. So this whole series of cuts that are cut into the side of this bolt is considered the threads, or the thread profile. So thread profile is really just if we were to take this and then cut it in half lengthwise, if we were just to come along and just kind of cut lengthwise down here, that what you'd see is a 60-degree thread profile. So the different profiles are unified, national, coarse, unified national threads. There's metric, SI metric threads. There's special 60-degree threads that maybe you'd see kind of in a micrometer or something. And then we have Acme buttress, brownish sharp threads, which are kind of square shaped. And then we have our pipe threads. So those are all the different types of thread forms or thread profile. Now looking at this fastener, we have a few different terms that we need to figure out here. The first one is the major diameter. So the major diameter is from the outside to the outside on the other. So that's our major diameter. And then if you look inside, we have the valley of the thread here. It goes all the way inside. So if we go from the inside, or the root, which I'll define that in a second, so the inside to the inside, that's going to be a little bit of a smaller distance from the inside to the inside, and that is the minor diameter. Okay, so the major diameter is from the outside to the outside, and then the minor diameter is from the inside to the inside. So the minor diameter, depending on the tolerance or the class of fit, is usually going to be slightly smaller than your drill tap size. That way the tap is actually going to cut that root of the thread out for you. Okay, so looking at the actual thread form, we have this is, if we look at the angle of the thread here, that is our thread angle. And that is 60 degrees for ISO and UN thread profiles or thread forms. The next that we want to look at is one pitch. So one pitch is going to be from, the pitch of a thread is from one point to the corresponding point of the next thread. So that's going to be our pitch. The next one that we'll look at is inside each one of these threads, there's a few different terms. One is the absolute point of the thread here. That is going to be referred to as the crest. Okay. And then if we go right into the inside here, right into this here, that's the root. So we have the root and the crest. The face of it, the face of a thread, so the actual mating part that's going to hit on the other side, that's called the flank. So to recap, we have our minor diameter, our major diameter. From one thread to the corresponding point to the other is our pitch. We have a thread angle of 60 degrees. That 60-degree thread form has a root, and then the tip or the point is called the crest, and the point that's in, or the surface that's in between here is called the flank. The flank is what's going to, of an external thread, is what's going to react against the internal threads of a nut, the flank of a nut. Okay, let's talk about thread forms. We have some basic thread forms here I want to show you. So we have a Unified National Coarse and a Unified National Fine. These are both 3/4 fasteners. So this is a UNC. This one here is a UNF. So the Unified National thread form has a angle of 60 degrees. The only difference being that a coarser thread is a little bit stronger and has like a fewer threads per inch. A finer thread has the same angle but fewer threads per inch. Okay. These ones are used mostly for controller adjustment, whereas these ones are more for tightening and fastening two pieces together. Then we have a metric thread. So this is an ISO or SI metric. And that metric thread also has a 60-degree profile on the thread. So they're very similar. The main difference that you'll see in these guys is the metric threads have an 8.8, and so they have numbers on the end to designate the grade, whereas a UN or Unified National will have dashes to represent the grade of the bolt, which was covered in the last video. So those are the main ones that we have. We also have square threads, Acme threads, buttress threads, Brown and Sharpe threads. So here's an example of a Acme thread. So Acme threads have a slight, very, very slight angle on the flank, and then they have a squared off crest. These are good for clamps, vices, that kind of thing. They're robust, as in they don't have a point that if something drops and nicks it, that it's gonna muck up the fit between the internal and external. They're quite strong, and then the actual, they won't lock up because the actual push is coming straight in line with the axis of the screw. So here we have a worm and wheel gearbox. This is a Brown and Sharpe thread series. So you can see that this is the input shaft on this gearbox, and it reduces the output shaft. So you see that there's a wheel here, and then if you look down in there, it's called a worm gear, but the truth profile is a Brown and Sharpe. I'll give it a turn there so you can see it. So Brown and Sharpe is very similar to Acme, but it can be throated, non-throated, or just straight thread. And so that's the best that I can show you. This is just a little gearbox we have with a plastic clear cover on it. So that's where you'd see a brown and sharp thread. All right, let's look at pipe threads. Pipe threads have a different function than a standard bolt. They are designed to seal between the internal and external. Now when I put my ruler across here, you can see that if the pipe sidewall is coming straight in line with the edge of the ruler, the threads are actually tapered. So that taper is across the distance of 1 foot. So if we went 1 foot in length, we would see a change of 3/4 of an inch. Okay, so 3/4 of an inch per foot taper on a national pipe thread. Now, national pipe threads have a slightly different function than national pipe thread fuel. Okay, so MPTF have an standard MPT thread is going to seal on the flank, whereas a petroleum or a fuel line pipe thread is actually going to seal in the roots and crest. So they're slightly different thread forms, so you have to be careful not to intermix them. That's just the way that they go together. So these will need some kind of a sealant, usually Teflon or pipe dope or something, and they go together. So those are pipe threads. All right, so the unified thread form is pretty straightforward. A pitch is from one point to the corresponding point of the next tooth. Okay, so that distance from there to there, that's going to be your pitch. The next major dimension that you want to know is that the crest actually doesn't come to a perfect point. It has a flat on it, and that flat is 1/8 of the pitch, 1/8 P, or 0.125 the P. The angle here is always going to be 60 degrees, okay, which makes this 60 and this 60, right? And the root is also, so if this is 1/8 of an inch, the root is actually going to be slightly larger, and it is 0.25 or 1/4 the pitch. Okay, the thread height, so the height from the crest down into the root, is 0.541 of the pitch, so a little bit more than half of the pitch. And these are all standard sizes and dimensions that bring that are the standard across industries. So the standard organizations are like, you know, SAE, the Society of Automotive Engineers. You have SI, which is Standard International. You have ISO, which is the International Standards Organization. And then you have like for anything fuel and oil and gas related, you have the American Petroleum Institute. So all of these bodies are just to set a standard so that you have interchangeable parts across industry. So these dimensions are part of that for a unified and ISO thread form. So just remember that 1/8 pitch, 1/4 the pitch. This one isn't as important to remember that decimal, but just remember that it's a little bit more than half the pitch for the height, and yeah, 1/8, 1/4, and then it's a 60-degree angle thread form. So for a standard unified national bolt, there are 3 main classes that you'll see. The first class is a class 1. You'll also see a class 2, and then you'll have a class 3. And then of course you remember that there is an A class for external threads, and then there's a B class for internal threads. So you can have a 1A and a 1B, a 2A and a 2B, a 3A and a 3B. So those are the three main classes. A class 1 thread is for really loose parts where you just want to spin stuff on and spin stuff off and assemble, disassemble really quickly, whereas a class 3 is actually size for size, or maybe even a slight interference fit, so that you actually have to spin the nut and cap screw to make the fit. So this is the loose end of the class fits, and then this is the tight fit. This class 2 is your standard. So these most bolts in a bolt bin are going to be a class 2, which means that it's got a slight amount of slop in the threads, but for the most part, you can just kind of spin them on and off. So metric or ISO thread have different, they don't have the same type of system as the Unified National thread profiles do. These ISO thread classes have a system where they look at the internal thread form. So if this is the cap screw, they look at the pitch diameter. So the pitch diameter is the line that goes through the threads where the distance between the flanks is equal to the thickness of the actual screw itself. So this would be X, and then this would also be X. So these are the same distances. So that's your thread diameter. So they look at that distance, and then they also look at the major diameters. And then they look at the nut. So if the nut is threaded on top of here, they're going to do the same thing for the nut. On the nut, they're going to look at the distance on the pitch diameter, and then they're also going to look at this diameter of how the smallest diameter. So it would be the minor diameter on the class A thread, but it's the major diameter on the nut. And basically they look at that, and then they factor that in for the absolute fundamental deviation from what would be considered the standard, and then look at that. So I'm not going to get into all of it. That's something that you'd have to reference in a book. But I do want to say that these thread classes go from E and F. Okay, so F being the capital F is your nut, and the lowercase e and F is the bolt or the cap screw. Okay, so lowercase is the thread class for the lowercase e and F is the thread class for the bolt. The capital E and F is for the nut. Okay, so this E's and F's are combined with, those are your tolerance classes, and they're combined with your position and your grade makes up your thread class. So these would be your tolerance positions, E and F, that's your tolerance positions. And then compared to that, you'd look at your tolerance grades. So your tolerance grades is going to be a number between 3 to 9, and that's going to tell you how much of a deviation that you have in between these two. So there's going to be a 3 to 9 number. So E to F is loose. And then you have G, which is your kind of standard. That would be the equivalent of a class 2 in the UNC. And then if you get into very fine tolerances, then you're going to be looking at H. Oops, that should be a lowercase h and H. And so these ones are like size for size. So this would be the equivalent of a class 3, this would be a class 2, this would be a class 1. So what I'm getting at is ISO classes have a little bit more complicated system where they actually look at the range where it should be, and then from that there's actually a deviation of that can be measured with special micrometers or with wires and a micrometer. So there's different ways of kind of measuring that out. And the idea is that some fasteners have or require that precision type of interference fit to stop the fastener from coming loose. So just understand that ISO classes have these different positions, and they also have these different tolerance grades, and then that's going to come up with the positions and the grades gives you your class. Okay, let's talk about some of the terminology that you need to understand when we are talking about the application of fasteners. The first, toughness, hardness, malleability, ductility, and elasticity are five properties of metal, and then these three here, the tension, compression, and torque, are forces that can be applied. So let's talk about toughness. Toughness is the resistance to fracture, or the amount of energy a substance can absorb before it breaks. So a piece of glass is an example of something that is not very tough. And another example of something that's not very tough in industry would be cast iron. It's not very tough. It can crack and break quite easily. Steel, or some kind of tool steel, a railway, an anvil, something like that can absorb a lot more energy before it breaks. And that is the kind of the key definition of toughness, is how much energy can it absorb before it is going to break. Hardness and toughness get mixed up. So the next one is hardness here. So hardness and toughness can get confused a lot. Hardness is different from toughness because it's solely the ability of a material to resist penetration. So if we have a piece of hard steel and we try to drive a prick punch or something into it, if it's hard, we're not going to put a very big dent into it. So that would be like some kind of hardened steel. But if this was aluminum and then we drove a hammer into our prick punch and then it dives down and gets pushed down further, it's not as hard. So different materials have different hardnesses. So the hardness is the resistance to penetration. Malleability is the ability for a material to be molded or hammered out into a sheet. So we in the shop have been working with brass rivets lately, where we are peening over a soft metal and it's kind of flowing and being hammered out. So malleability is that ability to kind of be rolled out. And you can see this, the malleability, if you strike the back end of a chisel and then you see that mushrooming over on the back end of a chisel, that's caused by the material's malleability. So if it didn't have that malleability and you hammer on the back of a chisel, instead of flowing and mushrooming, what is going to happen is it's going to crack or it's going to fracture. Okay, so hardness and malleability are kind of almost opposites to each other, right? Something that's really, really hard is going to be able to be hammered out flat and smooth, and hardness is the resistance to penetration. Now, ductility is a big one here, and this word is an important one. So ductility is important for fasteners because when we tighten up on this nut, what's happening is we're pulling and we're putting tension, and we're going to talk about tension in a second, but we're pulling this apart. When we pull that apart, this metal wants to stretch and kind of almost neck out. So ductility is the measure of how much a material can be deformed or drawn before it breaks. So a metal that has high ductility can be drawn through a die and it can be turned into a wire. Materials that don't have high ductility, if you try to draw them out or try to lengthen them, they are going to snap or break. And when we do forging or heat treating or working with metal, a lot of times in foundries or in manufacturing, they will heat up a metal and to increase its ductility and increase its workability so that it can be drawn out or rolled out much easier. Elasticity is one that's a little bit easier to remember. Think of elasticity as as an elastic band. Okay, so if we have an elastic band and we grab that and we stretch it, elasticity is not necessarily the ability of a material to be stretched. Well, it is the ability for it to be stretched, but more importantly, as elasticity is its ability to, when you let go of it, to come back to its original shape, right? So there's two properties there, like its ability to kind of deform and accept the new amount of stress that's being applied to it, but then also to, if you let it go, for it to return back to its original state. So a balloon, if you've ever blown up a balloon and then let the air out, you notice that the balloon doesn't quite go back to the same original state. It's kind of stretched out. So it's elastic in the sense that it stretches, but then when it comes back to its original state, you realize that it does have a limit to how much elasticity that it has. And that elasticity, the difference between an elastic band that you stretch and then let go back to its original versus a balloon that you blow up that doesn't come back to its original shape, is something called the elastic limit. And that's the maximum amount of tension that an object can sustain and still return to its original shape. Why that's important is for a fastener, if we over torque it and we stretch a fastener beyond its elastic limit, when we loosen it off, it's not going to return back to its original shape. It's actually going to stay elongated. Okay, so let's talk about the three main types of forces that can be, or stresses that can be applied to a fastener. Tension is when we take our fastener and we apply tension, is that we're pulling it from both opposite ends. Compression is the opposite of that. Compression is when we have our fastener and we apply and we put it in compression in this way. So tension and compression are two opposite terms. And a lot of times you'll see compression as an example in a beam or some kind of a static where you have the end supported and you press down on it. You're gonna see that this top part is going to be in compression, but the bottom wants to come down and flex out, and the bottom is actually going to be in tension. So tension and compression are opposites to each other. Concrete has a high amount of compressive strength, but has a very low tension. That's why we put rebar in concrete, so that it can take the tensile strengths that's applied to it. But rebar doesn't have a high compression strength, because it'll just bend and twist if you put it in tension. So those are some of the main terms. There's a few more to come here. Okay, so torque is a measure or applied force of turning or twisting. So torque is really defined as a turning force. And we have a center point in the middle of the fastener. When we put a wrench on it, and we apply a force to our wrench, we're really putting a torque or a turning around the center axis of that bolt going around. So that go off the page so it looks a little better. So that is essentially a torque. So torque is measured in foot-pounds or Newton meters. Okay, Newton meters being the metric, foot-pounds being. So the idea is that if we had a weightless wrench and we applied, say, and we hung 10 pounds off the end of it at 1 foot from the center of the bolt, we would have 10 foot-pounds of torque applied to that fastener. And that's really important, because that torque that we apply to the fasteners is going to tighten up So if we apply a torque to this guy, it's going to tighten this nut up, which is going to apply a tensile force, or apply tension to that fastener. That tension is going to stretch the fastener, which is going to test its elasticity. And there's a certain point in time where we reach what's called the elastic limit. Okay, so let's start off with elasticity and elastic limit. So elasticity is the ability for metal to stretch, and the metal does stretch a lot. And the elastic limit is the point where we stretch the fastener so far that it won't return back to its original state. So if I take this fastener and I crank up on this nut and I crank on it, and then I put the biggest wrench I've got on it and I over tighten it, this metal is actually going to stretch, and the little crystals inside of the metal are going to fracture, and it's going to kind of break apart, and it's going to stretch and be pulled apart. When I tighten that up, there's a certain point that it's going to be, if I loosened it back off, it's going to go back to its original size. But if I turn it that little bit more, it means that I've now stretched it to that point where if I loosen it off, it's not going to go back to its original length. And that's called the elastic limit. So the elastic limit is how much stretch I can put on this bolt before it gets permanently deformed, so that it's permanently elongated or stretched. So elasticity and the elastic limit are two different points. So with a fastener, you'll have the elasticity and the elastic limit. If you get into the elastic limit so that it won't return back, that's okay. A lot of fasteners are one-time use, where we're going to use them one time and then we're going to throw them away after. Being inside that elastic limit is going to give you the maximum amount of strength of that bolt. So that's the elasticity and the elastic limit. So the tensile strength, the more tensile strength we have, the more it's going to stretch. If we stretch it too much, we're going to get into the elastic limit. That means that it's not going to come back to its original point. Now there is a maximum or an optimal amount of tensile strength or stretch that we can put on a bolt, which is the proof load. The proof load of a fastener is the highest recommended tensile load for that fastener. It's within the elastic limit of the fastener, and it's measured in PSI or MPa. The proof load is slightly less than the yield point. Okay, so the yield point is another big one that we want to talk about. The yield point is the point in which a fastener suffers permanent deformation when a tensile load is applied. The yield point is just beyond the elastic limit of the fastener material and is lower than the ultimate tensile strength. The ultimate tensile strength is the point that it breaks completely. Okay, so if we look at our bolt, we can chart this. Okay, so we can, if we make a chart, we can say that this is the amount of load, or how much the fastener can absorb. Okay, so this is the load of a fastener, and then on this axis we're going to put the stretch. Okay, so when we stretch a bolt, we can actually apply a lot of load to it, and it's going to reach a certain point where we're going to cross over the elastic limit. Okay, so the elastic limit is the last possible point where we stretch the bolt where it will return back to normal. So we're going to hit our certain point, and then we're going to go a little bit further, and inside of here, inside of this, just barely, that's going to be our proof load. Okay, so that's our proof. This one here is our proof load. And this one here is our elastic limit. Once we get past that, you're going to see that the actual amount of load per stretch, so we can stretch it a lot further, but the amount of load that this is going to take is actually going to be minimal after that elastic limit. So once we get into that point, there's a point here where this dives off, and this point here is actually called the ultimate tensile strength, or the yield point. So the yield point is that we can stretch and we can probably get a little bit more load out of the bolt when we stretch it past its elastic limit, but at some point we're going to stretch that bolt and it's just going to start breaking, it's going to fracture. And the yield point is not much past the elastic limit of the bolt, and we're not going to get a lot, but you can keep turning and turning and turning a bolt. Now bolts and fasteners up into, so from, let's just say 0 to 3/4 of an inch, are greatly over torqued in general in industry. And everything from 3/4 plus is generally under torqued. So that's why, if you were just to do it by hand. So that's why it's really important when you're dealing with fasteners to keep in mind when you're dealing with small ones that you can really quickly and easily overstretch them and neck out a bolt and get inside of this zone that you want to stay out of. So this would mean like we're stretching, we're tightening, we're tightening, we're tightening, it's going to get tight. At some point we're going to stretch past. If we loosen that off, the fastener's not going to go back. And inside of this area there's going to be a certain point where this is just going to drop off and it's going to break. If we stretch it too far, it's not going to be able to hold off any amount of a load. So shear strength is when I have a fastener. If I have a fastener and I bolt it, let's say in between two flanges, and one of these flanges wants to go in one direction and the other one wants to go in the other direction, it's going to apply a shear stress right in the center of this fastener. So shear stress is usually about 0.6 times the tensile strength of the fastener. So it's something that's going to shear a lot easier than if you were trying to yield it in tension. So that's shear. Shear is the action of a material being pulled apart in two different directions at a single point. Okay, so I'm drawing here I want to talk about fine thread versus coarse thread, to kind of just touch on some of these ideas and principles that if we're tightening up a nut or a thread or a nut or a cap screw, these two are going to be put in opposing forces. So the load or the point that's going to take those loads or those forces are going to be the flanks of the bolts. Now, it's important to understand that the flanks and these threads are going to be put in shear. So this nut is going to put a shear force kind of through this plane where it wants to shear and pull the teeth off here, whereas this internal minor diameter to the inside of the nut is going to be wanting to pull this in the opposite direction. So there's kind of a shear force that's being applied there. Another thing to keep in mind, so that's one thing to remember is shear force. The other thing to keep in mind is those opposing forces. If we have this one coming down and this one going up, and it's acting on this angled surface, what's going to end up happening is a portion of this is actually going to be pushing the nut out this way, and part of it's going to be pushing the threads of the cap screw in that way as well. It's like a wedge, right? It'd be like if I had two wedges and I'm pushing them against each other, they're going to slide. They can't go down, but they can stretch outwards. So that's something called nut dilation. Okay, so when you tighten up a fastener and you tighten up a bolt, the nut is also, the cap screw is going to stretch, but the nut is going to dilate and go in. It's like dilating your eye or your pupil, right? Like they dilate and they go larger. Same thing as with a nut, it goes larger. Okay, so those are different things to keep in mind. Now, going back to the fine versus coarse thing, when you have a coarse thread, you actually end up with a smaller minor diameter. So the minor diameter of the threads on a coarse thread is actually smaller. If these were fine threads, the minor diameter is going to be larger out. So the tensile strength, technically, of a fine thread is larger than a coarse thread because the root diameter, or the minor diameter, has more surface area. However, with a coarse thread, you have a wider tooth. So you have basically more material here on the thread to resist that shearing force that I was talking about. Therefore, a coarse thread actually has more strength in like shear strength than a fine thread. So fine threads, the teeth will shear first, but there's more strength inside of the mass of the cap screw, whereas coarse is going to have a stronger shear strength. So the SAE has designated, while you have like a grade 5 bolt, you can say that a coarse has a strength of 120,000 pounds per square inch. The automotive has designated fine threads as being 109,000 pounds per square inch. And really the only reason for that is that when you have smaller teeth, you have less material to resist that shear strength. So you have to kind of reduce it. So for fine threads, you're going to be looking for areas where you can position something. Coarse threads are what you're going to use for fastening machine parts together.